So I want to do a problem illustrating some question that was asked towards the end of the lecture. I sort of sketched some graph and gave some explanation. Perhaps it was uh, it was all very rushed. So, and I was drawing um, um, some function. I mean, capital F of X. All right, but just uh, without working with any specific thing. Perhaps it may be better if I work with a very specific function and illustrate the concept in that case. Yeah. Okay. So the question is the following. So given f of x, which is satisfies satisfies the condition for it to be a distribution function. Okay, find a random variable x such that of x is equal to fx of, or I can just simply say given a distribution function. So you can put this in parentheses. Given a distribution function, I have already told you it's a distribution function. Find a random variable such that this happens. I suppose this was a question. Not sure. So as I understood it, I suppose this was a question. Uh, okay, so you don't have to construct. Yeah, I mean, this can be answered in several ways. You already know that this is a distribution function of some random variable, and you need to find your x. Okay, okay. So how do we do that? You just have to reverse engineer the way of finding distribution function for a given random variable. Let me work out a specific example. I think that may be very helpful. So suppose that, so I just work out an example. Let f of x be defined as, so just let me write here. So I'll take a fairly simple looking function. So if x is less than 0 and it is half, if 0 less than or equal to x, I want to take something which is not distribution function of a continuous random variable or a discrete random. It's a mixed type. So I deliberately make things a little complicated for myself. So let us write here 3 by 4. If, yeah, I mean, you can write anything here. So half less than or equal to x less than, let us say, 1. Okay. So you have reached up to 3 by 4 and you have 1/4 left. And let us have another jump to discontinuity. So let us say 9 by 10 plus some number I have to write here. Let me write here something. Mm, so x minus 1. Okay, times some c, which I will write in a minute. So maybe just write 100. Doesn't matter, you can put some number 100. So uh, this is valid if 1 is less than or equal to x, less than or equal to some number, okay, less than or equal to some number, and at that value this whole thing should become 1. So this must be equal to 1/10. So x minus 1 times 100 must become 1/10. So x minus 1 should become uh, so 1 by 1000. So 1 plus 1 by 1000. Okay. So 1001 by 1000. You can check that it becomes 1. And after that it stays 1, of course. X bigger than or equal to 1, it stays 1. So this is like the continuous part from here onwards, but up to here some discontinuities. So this is a type of function I was drawing the other day, except that this time I have very specific numbers. So you can understand, you can sketch the graph and find out what is happening. Yeah, I mean, so for a this already puts a lot of restriction on what can be your omega and so on and so forth. If you are given such a problem and you just want to come up with a distribution, okay, a random variable with these properties, okay, so you just give yourself some numbers. So you see, this is the fact that okay, let me draw a graph once, maybe just very briefly. So the fact that there is a jump discontinuity at here, so at what, 0, I suppose, yeah, 0, already indicates that there is a point mass at 0, okay, and again at half there is again some there is a jump discontinuity. In between nothing happens, so in between it looks like a step function. So this is uh, yeah, 0, half. Didn't mean to spend too much time, but okay, let's just draw 3/4 here. mm. Now where is the next one? It stays okay, 3/4 until 1, so this is like 1, I suppose, and then there's a steeping. Okay, so at 1 it becomes 9/10. Okay, maybe here somewhere, 9/10, and then there's a steep increase up to the point where you hit 1, and from then onwards it just stays 1. This is your function. So this is not drawn to scale, but this is how it looks. Okay, yeah. So okay, so this is it. So what you can do is, what does this mean? This means that probability of x less than or equal to 0 is actually equal to half, but probability of x less than 0 is actually 0. Okay, so that's because of this first condition. So this is what I mean by saying that probability of x equals 0 is actually equal to 1/2. And so it has some discrete behavior like this. Probability x equals half is, well, x less than or equal to half becomes 3/4, but this is already 1/2. So this has to be the difference, which is 3/4, because in between there is no change. So sorry, 1/4. Okay, 3/4 minus 1/2, that's 1/4. So again, discrete behavior. And then probability x equals 1. Probability x equals 1, likewise you compute. So 9/10 minus 3/4, whatever that is. Okay, 9/10 minus 3/4, whatever it is. Okay, and from then on, it behaves like as if there is a, you know, some yeah. So you can do this type of thing. So uh, yeah. So now you should write here something like a density function. So okay. So this is now, let me say what happens. Okay. So let me say this. Probability of is what I was doing towards the end of this. 1 less than or equal to x less than or equal to t. I mean, now this side it's more like, yeah, this t here, this is equal to, so okay, let me put here, I think maybe erase this. This is equal to probability. So t is bigger than 1. So you see, and we'll assume that this is bigger, less than 1001 by this thing. So it will become clear. I'll write this clearly. So this is equal to probability of t, of course, minus probability of 1. And in that range, it becomes like 100, whatever it is, 100 times x minus 1, 100 times x minus 1. So this happens in this range, 1 less than or equal to x, less than, uh, I can put less than or equal to, it doesn't really matter. So 1001 by 100 by 1000. Okay. So this is how it is, and you just, so this is, you have your density function here like this. Okay. So it's like this x is uniformly distributed in this tiny interval, not drawn to scale, of course, 1001 by 1000. In this, the density function looks like 100 times x. Okay, it's a constant, in fact. It is just a constant. Um, yeah, it's a constant. This is the density function. Okay, so that is it. And mm, yeah, so well, if you are asked to give an x, so this is uh, yeah, this is a random variable. You have defined your random variable, or rather you have said how this is uh, you know what are the values that it takes. Random variable takes a value ha sorry, so it takes a values 0, half, 1, and then all values between whatever, here to here, and that's it. Okay, you can think of it that way. That's it. And then yeah. And so if you are asked to give a specific model, so specific probability space, omega whatever f p. So we usually don't bother so much about omega, but omega will become clear from the context. You can take. So I want to do this explicitly because this is important for your general understanding, because otherwise you just will learn a lot of theory and learn to do some routine problems, but conceptual understanding is lacking, and that's not good. So it's okay if I spend 15 minutes on this. So you keep your omega as simple as possible. Okay, how many points do you want your I mean so x to take discrete values 1, 2, 3. Okay, so you just take omega, take omega to be discrete 0, 1. Okay, I need not have put 0, but I put already. I'm not going to change, correct myself. 0, 1, 2. Why 3? 3 is not needed. Okay, and then union. And you can just take any interval, it doesn't really matter. Okay, so yeah, so let us take the interval 5, 6. Okay, just for the fun of it. And what is this f? F consists of all subsets of this, and it also consists of open open intervals of this 5 to 6. Okay, and that's it. I mean, uh, you don't have to say anything more. Well, the fact that f is a sigma ring already means that these sets, well, the f is generated by these things. You can take that to be the your f anyway. So you would like to, of course, associate masses to this. Probability of 0 is equal to, what would you like it to be? Just half. Probability of 1, you just keep it simple. So probability of 1, you like it to be 1/4. Sorry. Becomes a little messy. 1/4. And probability of 2, you had that number already. Uh, so 9. So let's simplify. This is a very simple fraction. 40, 36 minus 3, 33. 33/40, right? So 33/40. Okay. So, and then what about here? And you just keep it to be uniform. By the way, you could have included the endpoints. It really would not have mattered. So probability of some b, a comma b in that interval, a comma b, this is equal to b minus a by 1, but you have already taken so much, so this must be shrunk to its size, because you have only left out 1/10. So this should account for the total probability for this set should account for only 1/10. So you write like this. This is for phi less than a, phi less than a less than b less than 10. That's it. And this describes your entire probability space. Okay, now what is your x in this one? It is just, so you see, x carries, so x carries, of course, there are many ways of doing this, but at the moment, you keep everything simple. X carries 0 to 0, maps 1 to, I think here, next jump discontinuity was at half, so I put half. So this type of thing, can play around with it. This is what I mentioned. So 2 goes to, well, the next jump discontinuity is at what point? Okay, so 1, put 1. And then what about 5 to 6? I mean, you have an option now. You can, yeah, uh, well, I mean, let us say this entire thing should account for 1/10 probability, no? So you find a, so on 5, 6, x is given by, so okay, So x maps, so x maps 5 comma 6 is, keep it simple, to what? Open interval 1 to 1001 by 1000. Uh, but maybe some scaling is required, but I map it like this. I think then this should work, I suppose. Or maybe it is 100 times, I think. Because as x varies between this interval, you have to pick up the whole thing. So I think maybe it is 1 by, it is 100 times. Yeah, 100 times. Okay, so this maps like this. Uh, I think this will be, so there's a limit speed at which it is described. One could do this. So yeah, so t. So if it is okay, so here if I take x, so t goes to t minus 5 plus 1. So so it has to divide by 1000. So it's just some scaling is going on here. Uh, okay, and then so I think it has to be scaled appropriately. That's the only thing. Once you do that, it should give you the correct probability. Yeah, I suppose. So I'm not sure if I should. Yeah, this you try to work it out so that, so this will anyway be a map of the form at plus b. Okay, a and b are constants, and what you want is that after you do this transformation, as you go, as x goes from, so x varies from here 1 to 1001, this one, it should give you this answer, right? So uh, so that will tell you, I think that should match with the uh, what I'm saying is the probability that x varies in this range. Okay, x varies in this range. That is given by this. Uh, yeah. So what do you want? You want this following thing. So 1 to t, 1 1 to t. Or maybe I write here. Okay, 1 to t. What is this? X by 1 to t, x times 100 minus 1. This must be uh, dt. So here's something. I didn't work it out here. So here, whatever this is, x takes a value 1 to t. What should I write here? Some f of t, f of x dx. This we already know what it should be. This must be 100 times, it must be a function of t, so t minus 1. Okay, and in this interval, 0, no, not 0, sorry, t is between 1 and 1001 by 100. 1 less than or equal t less than or equal to 1001 by 100. On the other hand, so this map, so we know this must equal, so whatever it is, this must equal the set, okay? whose measure is already given to you, uniform measure, etc. So this must be probability of the set ET. Okay, what is ET here? ET corresponds to the set so set of all omega such that, well, so x omega, that is AT plus B, must be between this. This is all that you need to do. It's just a simple calculation of what A and B should be. It must be a linear isomorphism, but I didn't want to compute this. So this must be between where and where? Yeah, so one, this must be 80. So 100 times t minus 1, x omega, hmm, is between 1 and 100 times t minus 1, I suppose. 1 and t, just up to t. Yes. Okay. That's exactly the definition, after all, of capital F of t. Okay. Using capital F of t, this is what you should get. From here, you can just fix this A and B business. No problem. So, okay. So that should give you understanding of so compute A and B.
Thank you, sir.
Compute A comma B this way. Okay, fine. Let us move on. Yeah, things are simple to understand once you understand it, but when you work out specific problems, specific numbers, with specific numbers, you have to be careful. It takes a little time. I'm particularly slow with computation because in the usual life of a research mathematician, hardly ever do we do this type of calculation. I'm really spoiled by having spent most of my time in a research institute where we teach only PhD students. So this type of calculation is really, I mean, not that we don't know, but it takes time for us for me particularly, to spell out all the details. Anyway, I hope this gives some better understanding. Okay, so now let us move on. So I was talking about expectation, and we saw some basic properties of expectations. I'm not going to recall all those things, but let me continue. One of the things we did was, the central moments and then central moments. We did all these things. So sigma k, and then we had variance of a random variable, so denoted var x. So variance of x is uh, this is um, yeah the x minus, so the moment about the mean. That's a way to remember it. Second moment about the mean. So m1 whole square. So this is equal to expectation of x minus e of x, the whole square. And we worked it out to be expectation of x square minus expectation of x. This is just a number. You just square this number. Sometimes we put the parentheses, sometimes we don't put the parentheses. The meaning is very, very clear what it is. Okay, fine. Now, so we also saw that expectation of ax plus b, ax plus by is equal to a times expectation of x plus b times expectation of y. Okay, but what about expectation of xy? So is it equal to this product of the expectations? That's not true in general. Okay, simple examples can be computed, but we have the following. So not true in general, not true in general. Okay. However, so lemma or whatever. Suppose that x and y are independent. So at the moment we are only working with discrete random variables. Discrete random variables. Then expectation of xy is equal to expectation of x times expectation of y. Okay. How to prove this? The main point here is that, um, yeah, so set let z is equal to x times y, and let us just compute expectation of z. Just apply the definition. This is equal to summation z times probability of z equals z. Okay, so this is equal to summation z probability of xy. Well, okay. So we need to understand this set z equals z. So okay, yeah, xy. So let me write here x equals x and y is equal to y, which we write like this, and summation over. So I just skip a few things. X times y is equal to z. Okay, but now this is equal to summation over z in real numbers, of course, and summation over x comma y such that xy this is equal to this. But whatever it is, xy is equal to z. Now this is now here you use independent probability of x equals x and y equals y. That is probability of x equals x times probability of y equals y. So sorry, I left out a z here. Y equals y. Okay, and now you change the order of summation. So I'll just display that here. So this is equal to, see, after all, the sum is going to vary over all possible real numbers. And here x and y, you are going to vary arbitrarily, so that x times y equals z. You may as well just simply write summation. In the place of z, you write xy, and then just allow x and y to be arbitrary. You need to think about why this is same as this. Probability of x equals x times probability of y equals y. And everything is absolutely convergent, no problem. Now you see you can write this as probability of x times probability of this, x varying in real numbers, times summation y in reals, y times probability of y equals y. Okay. And this is expectation of x, this is expectation of y. Okay, now, yeah, so what do I want to do? Yeah, so now this suggests a definition. Okay, rho of x comma y, this is called covariance. Covariance of x comma y is defined to be e of xy, sorry, e of x times y, there's no x comma y. E of xy minus e of x times e of y. Uh, no, sorry, this is not covariance. is I think it's called correlation. Covariance is this divided by something, variance of x times variance of y, but at the moment we just define this correlation of x comma y. Okay, define. So this is definition, correlation of x comma y. Okay, is defined as the following. Okay, now if correlation of x comma y equals 0, we say that x and y are uncorrelated. Yeah, uncorrelated. Correlated. Okay. Of course, the independent random variables are uncorrelated. That's what we just now proved. Okay. Uh, yeah. Uh, okay. So, hmm, so just like we saw some basic properties of expectation, the next we list some properties of variance. Hmm, variance. Hmm. So, what is variance of a times x for a constant x a discrete random variable? At the moment, we have defined only everything discrete. Okay, so this is equal to a square times variance of x. Okay, and what about if x comma y are independent random variables, then so at the moment we are only saying discrete. Okay, then variance of x plus y. This is an extremely useful formula. Is equal to variance of x plus variance of y. Okay, and notice that because of the square here, so note variance is not linear. Variance variance is not linear. Okay, even variance of 2x becomes 4 times variance of x. It's not 2 times. Okay, so I think I can safely leave this to you, but this one let me prove. So proof. Let me write here 1 and 2. Proof of 2. So just apply the definition. What is variance of x plus y? This is equal to, yeah, so expectation of x plus y whole square. Sorry. This whole square. And then I should put a round bracket here. Minus expectation of x plus y. Now this time I put round bracket, but here. Okay. But what is this? You just have to expand. So this is equal to expectation of expand this. By the way, is it clear what is the meaning of x times y and so on? We have seen more complicated things, but I hope it's clear what is the meaning. If it is
Yes.
not clear, you have to ask me. Otherwise, I would think that you all understand. E of x plus y is e of x plus e of y. So I write that and put the square here. This is equal to, well, expectation is linear. So e of x square plus 2 times e of xy plus E of y square minus, and then right here, you just, these are two numbers, just a plus b whole square. So it is E of x square plus 2ex ey plus, need more space. So E of y, I just squeeze it in here. Okay, square, and that's it. And this is equal to, okay, I have this and this, I can write that together. That becomes variance of x. And likewise, this and this, that becomes variance of y. And then I have 2 times E of xy, but x and y are independent. So that becomes 2 times E of x ey minus 2 times E of x ey. That's the leftover term. And of course, that cancels. And here you have used independence of xy. So if you like, I can write here, since xy are independent. Okay. So this term cancels and we get the answer. A simple enough thing, but it's very useful, variance of y. But suppose you are not able to cancel, then what happens? So nothing really, we just get 2 times plus 2 times the covariance of xy. That's all you get. So in general, okay, all right. I want to work out some problems. Yeah. So I need to look at the book for a minute because I didn't copy the problems properly. Just a minute. Hmm. Uh, so I want to work out. Okay. Uh, okay. So let me talk about this problem. So each member of a group of n players rolls a die. So there are n players. Each of them roll a die. Okay. And look at the numbers that show up. So for any pair of players who throw the same number, the group scores 1 point. Find the mean and variance of the total score. So this is a problem I want to discuss. Let me write down the problem here. So this is for your information. I don't remember the exercise set. I think it is, yeah. So anyway, so example or exercise. Uh, each member of of a group of n players rolls a die. You can assume it's a fair die. When nothing is said, you can assume it's a fair die. Okay. Anytime a pair of players throw the same number, the group wins a point. Okay. Find the mean and variance of the total score. Okay. So total score is a random variable. You see, it's a random experiment. I mean, you don't know how many, you are not told, you don't know how many pairs of players have thrown the same number. It may vary from one throw to the next. Sorry. So, uh, so you have a random variable. What are the values that it can take? It can take values from, you know, uh, 0 to n. 0, okay, 0 to not n, but some other number. Number of pairs. Each time a pair throws a same number, you win a, you score a point. So n choose 2. Okay, that's the maximum. So all of them suppose throw 5, 5, 5, 5, 5. Okay, then there are n choose 2 pairs, such that each pair has thrown the same number, and that means the group wins. The contribution for each pair is 1. There are n choose 2 pairs, so maximum that it can take value is n choose 2. So anyway, it's a random number, random variable. Okay, so so let S denote the, so is the way to answer this question. So solution or whatever. S denote the total score. Okay. Now what is asked is, even if you write this, so it gives some understanding of what exactly you need to do. Compute. So we want to compute this and variance. Yes. By the way, square root of variance is called standard deviation. I may have said that before, but anyway, at the moment, these are the things that are required to be computed. Okay. Now, so you need to be able to write S, yeah, as a sum of, I mean, sum of the scores, right? Contributed by each pair of players. So if the players are numbered 1, 2, 3 up to n, let xij be the contribution to the total score uh, for the uh, for the game. Okay, so this is equal to xij. So here you need only sum over I less than j, where, so then where, what is xij? Xij is equal to 1. Okay, if I comma j, ith and jth player through the same game. So let me denote the players by P1, P2. Okay, Pi and Pj throw the same number, same number. This itself is a random variable, you see, and 0 throw different numbers. Pi and Pj throw different numbers. Don't throw. Okay, same number. Okay, and now, so let me first do this expectation. So the expectation of S is equal to expectation of the whole thing, sum I less than j, xij, but expectation of sum is same as sum of the expectations. This is equal to, so let me write here summation xij, e of xij, sorry about bad handwriting, I less than j. Now you need to compute what is the thing. So xij, what is expectation of Xij? Okay. Hmm. So this is all. Once you compute this, you get the answer. And of course, so um, okay, let's just do this directly. But we know what Xij is. Xij is a random variable which we have already said. When it takes 1 and 0, so uh, so Xij. Hmm. Okay, so we need to compute this probability of Xij equals 1. What is the probability Xij equals 1? This is what we need to compute. And then probability of Xij, these are the only numbers it takes. So this is what we need to compute. What is the meaning that Xij equals 1? Okay, so this means that Pi and Pj throw the same number. So you just look at the ith player. Pi has thrown, let us say, some number A. Then Pj should throw the same number. Okay, so this A can be any number. There are 6 possibilities. B, Pj could have thrown anything, but his throw should match with this one. So it should be A, comma A. So, well, you think about it, it's exactly 1 by 6. You can think of it in more than one way. You just imagine for a minute that Pi throws the thing first, okay, and then Pj throws. So, whatever, irrespective of this, the favorable outcome is exactly 1 out of 6 possibilities. That is therefore 1 by 6. Or you may think that they throw simultaneously, and so all possible pairs, there will be A, comma B, 36 of them. Exactly 6 of them are favorable, 6 by 36. Either way, you get the same answer, 1 by 6. And this is, of course, 5 by 6. Okay. And now what is the expectation of this? This is equal to, yeah, huh. So, uh, 1 times, just write this, Xij equals 1 plus 0 times probability of Xij equals 0. Okay, so therefore expectation of Xij, it is good to write at least in the initial stages the entire step, I mean, starting from the definition and so on. Otherwise, it may be confusing if you go too fast. All right, so this is 1 by 6, no? Okay. Therefore, what is the probability? Sorry, we are now almost done. What is expectation of S? So for this is irrespective of I and j, of course, I less than j, and there are n choose 2 possibilities, n choose 2 times 1 by 6. This is n times n minus 1 divided by 12. And what about variance? We'll compute variance also in a minute. Just let me get some more space. Variance of S is equal to, okay, so you can compute expectation. So you can apply the definition, expectation of S square minus expectation of S the whole square. But if you recall, okay, instead you can do the following thing. Note that Xij, this is something we have observed, XKL or independent. Independent random variables. Okay, this is, I didn't scribble something here. Okay. Okay. Is that clear? Well, this was done earlier, Uh, so you, you you either you check it directly, or you anyway. It's very simple to check this. Okay, uh, each one of them is going to take values 1 or 0. You compute the thing, and it turns out that it's independent. Once you know it is independent, it's very easy to compute this one. What is variance of S? And we had this property too, right? Variance of x plus y is variance of x plus variance of y for two random variables which are independent. But suppose you have some bunch of random variables, you can repeat this process. When you have a bunch of pairwise independent, only pairwise, that will do. Need not be together. Pairwise, should they be together also? Actually, this is not together independent. Hmm. Gives me a pause. So, uh, you see, this is two distinct ones are independent. Hmm. So I suppose it requires some justification. This is variance of summation xij, xij. So, yeah, I think, hmm, or only pairwise list. You see, it's not like any subcollection is independent, that you can easily see. For example, if x12 and x21, x23 both are assuming the value 1, then x13 also assumes 1. So that already implies that they are not together. I mean, as a family, they are not independent. So one has to do this a little bit more care. I Yeah. Hmm.
So when we square, only two terms will come per
Yeah. So
term. Yeah.
maybe it has to be done directly. Okay. Hmm.
Square equal as sorry no xij sorry I got confused sorry.
Yeah, well, xij square equal, see, variance of xij is easy to find. Okay, because xij takes values 1 and this 1. But yeah, I mean, okay, so I made a mistake when I calculated it. I was working it out. I just blindly wrote that this must be summation variance of xij. This, I'm not sure if it is the case. So it gives me a pause. Why this is so? Because it's not as a family linearly independent. So the problem is that okay. So let us yeah. So let me suppose this is the case. Then it's if this were to be the case, then it's easy. You just compute variance of xij just using the formula. Okay, so this I put a question mark here. I'll come back to it. What is this? This is E of xij square minus E of xij whole square. So this is equal to x. So E of xij square, I have to write here. So I'll write it here. Xij square is equal to probability of, so xij square. This is probability of so this is okay. Xij square is actually xij, so this is just 1 by 6, I suppose. And whereas this one is already 1 by 6 and then whole square, so 1 by 6 square. This is equal to, so you can compute it, 35 by 36. Anyway, whatever it is, just compute it. Okay, so this is very easy. Then you just substitute that in here. So probability, therefore, if this is correct, so I put a question mark in here, variance of S is then will be, so n choose to 35 by 36.
I guess that's 5 by 36, not 35 by 36.
Huh?
Sir, I think it should be 5 by 36.
5 by 36. Yeah. Sorry. Not 1 minus, 1 by 6 minus. Absolutely. Okay. Thank you. Okay, good. Fine. So this is okay. But before that, so how to justify this? I'm not sure if that is correct, but so you need to understand variance of x plus y plus z. Okay, if x is independent of y plus z, then it's okay. You can do this again. So if x must be independent of y, x must be independent of y plus z, and y and z themselves must be independent, then you can iterate this. So I only know, so let us just do this mind game. So is this equal to variance of x plus variance of y plus variance of z? This is what we want to know. Okay. So in order to know this, if we know this, then maybe you can apply this successively or more generally. Suppose I have this. So assuming pairwise, I somehow think that it probably is not true. So x1, x2 plus xn. So the question boils down to the following. Suppose x and y are independent. I think we did this. x1, suppose x1 is independent of x1, x2, xn, each one of these. Okay, each of this. The question, so this is something for you to think about, for me also to think about. Question, is S x1 independent of x2 plus x3 plus xn? If the answer is yes, then it's easy. Okay, this is what we want to know. So not sure. So this, if you can show this, then you can justify that step. Otherwise, not. So I don't know. At the moment I will also think about it. I probably made a mistake in the previous thing. So otherwise, otherwise you just take a longer route. You compute variance of x square, and that's not very complicated because it's going to involve only maybe we will think about this. Okay, but let me complete the other problem because I at least write out s square is equal to summation xij whole square, and this is equal to summation xij square for each one of these, and then plus 2 times summation xij and then xkl. So ij, the pair ij, always we write I less than j, and this is not equal to so okay, so there has to be some ordering, otherwise this 2 should be given up. Okay, so you arrange it in some way, or most naturally dictionary order. So otherwise you just write xa not equal to x, not equal to kl. And yeah, so now you can compute this e of s square. This is equal to e of this xij square, but e of xij square is same as xij square is same as xij. That's clear. Because it is a indicator function of a specific event. So yeah, you use that immediately, or you just directly do it also. Either way, you just hit this plus expectation of summation expectation of this xij xkl. Any two of them are independent. Okay, ij not equal to kl. So since any two of them are independent, sorry, I cancel this and give something. Yeah, and so now I think we can make it. This is equal to, okay. I think that this is true without further hypothesis. You just have to compute it. This problem, whatever I said here, okay, I'll come back to that later. First, let us finish this. Now I see that this is summation E of xij plus this is these two are independent random variables, right? Any two of them pairwise they are independent. So this is summation E of xij times E of xkl kl. So distinct pairs. Okay, and therefore now you see E of s the whole square will have the same type of thing. E of s the whole square is summation E of xij whole square. Okay, so this is equal to summation E of xij the whole square. I think this is probably the correct way to do it, but I have something else to also say. So this is what is it? So this is all possible pairs I less than j plus summation. The pairs are distinct, ij not equal to kl. The same thing, E of xij times E of xkl. Okay, so you see these two factors get cancelled. Therefore, variance of x s is equal to whatever we have. Okay, this is already computed the first term. Okay, let me write without skipping the terms. So this is summation. So summation E of xij minus summation E of xij whole square. I don't know what I'm doing. So this is whole square. I hope this is right. This looks okay. So let us compute this. This is, we did it just now. This is expectation. So n choose 2 times. Was it 1/6? I don't know. Yeah. think, minus this one, expectation of x whole square. So this is again, n choose 2 terms are there, and 1 by 6 whole square. Okay, this is n choose 2, 1 by 6 whole square, 1 by 6 minus 1 by 6 whole square, which is 5 by 36. Okay, so I believe this is correct. Without any further hypothesis, each of, so let me now make this statement, which we can prove also. I'll prove it today itself. So this is a nice thing, I think. Variance of x1 blah 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 plus xn is equal to summation variance of xj. So this is also exercise provided x1, don't assume that any further condition, this is not required. I just cut it out. So this is not required. Let it stay as it is. I'm not going to erase it. But here, weaker assumption will do, or pairwise independent. That's all that is needed. Because you just do the calculation, you will have summation expectation of xi, xj. But because xi and xj are independent, it becomes expectation of xi times expectation of xj. You just do it. This is the correct thing. So this is an exercise. Try it at home. If you have difficulty, you can ask me either in the next lecture or during the tutorial hour. I think I should stop here for today. Sorry, I am going a little slow, but we will gain speed. Okay, already, yeah. I think I should stop here for today.